As we all know, the intersection of artificial intelligence and embedded systems is reshaping the way we approach product development. Today, we will be unraveling the possibilities that lie within TI's Edge AI tools and SoCs, showcasing how these technologies empower us to create products that are not only smarter, but also energy efficient. To shed light on this topic, we have with us Shyam Jagannathan, SMTS and Edge AI architect, and we're fortunate to benefit from his insights today. Let's welcome Shyam to the stage.
Everyone, unfortunately, I'm the guy standing now between you and the much-needed tea break. I'll try to keep the presentation short and maybe give us more time for questions. I'm with Texas Instruments for about 18 years now. I've had the opportunity to work on a spectrum of technologies, starting from video compression, image processing, computer vision, deep learning, and more recently we are coined this new term called as Edge AI. It's not a very new term, but it's not reached a level of maturity that it has really gone into a wide-scale adoption and full-scale production. Before I switch to my presentation, I'd like to just show you a short 1-minute video.
To meet the needs of our data-driven world, technology must become more capable, efficient, and intelligent. Nowhere is this truer than in Edge AI applications, where advanced analytics capabilities allow decision-making in the moment without the cloud helping analyze growing mountains of data. Edge AI is making our world simpler and our electronics more productive and safer. It keeps our world moving from point A to point B, whether that's in a room, heading across town, or on the other side of the world. TI Edge AI technology delivers the intelligence needed to help you design the next generation of smart products, making them smarter, scalable, more affordable. With the right technology, the edge can be more than just the end of a network. It can be where that network meets the modern world and carries it forward. Texas Instruments, making the future of embedded possible.
Okay, so this is roughly some of the points I'd like to talk about today. Okay, so does anybody identify this curve? This is called as a Gartner Hype Cycle. It's divided into 6 parts. So this is a very commonly used curve to refer to any emerging technologies, anything that is new. You might have heard of cryptocurrencies, blockchain, analytics, and so on. So this is something for analytics, and as it stands for 2023. So this is the first part of the curve where you get a lot of these emerging new technologies that, that are shown here. This is called as an innovation trigger, something like artificial general intelligence, which is AGI, you have generative AI, AI engineering, and so on, right? So this is where this is like very nascent and something very new that people have started hearing about. Now, when they hear a lot, like generative AI, you might have heard a lot about ChatGPT taking over the world. It's at its peak. So that is called a peak of inflated expectations. Then comes the reality where it's not really, we don't hear a lot about it, but there are some companies who have found value in those technologies and started experimenting. And this is, and that enters a phase called as a trough of disillusionment. So AGI is over here. Now, definitely it's not in the later part of the curve, it is the slope of enlightenment where people really know how to productize the technology and apply it wide scale, which is called as a plateau of productivity. So you might have used or come across applications which use computer vision to solve some kind of an automation problem or some kind of navigation or any kind of identification problem. But the challenge with computer vision was there was no uniformity. It was also a pro for that because there was a lot of researchers who could come up with specialized algorithms that is focused to solve a certain problem. Then came deep learning, which was like a hammer solution to a lot of problems, which had a certain structure, certain uniformity that was suitable for many people in the industry, not only to silicon providers, but also the software evangelists, and also something that people who have enough data, that's all you needed. So you only need data to go and train a neural network to give you some results that you want. So it's quite easier to adopt a technology like deep learning to solve any of your problems that you're trying to, you're trying to solve. So Edge AI is somewhere here today, and it's very much on its way to production, right? So many people are experimenting, trying to test its limits, and see how well it can be applied and how effectively it can be applied to solve their problems. To help, most of the people solve these problems, Edge AI is definitely applying artificial intelligence on the edge. So this is very much an embedded problem. You need an embedded processor with low power envelope, without need of much of active cooling, but with, significant amount of performance that it can really take on handling multiple, gigabits of data. So this is a scale of processors you might have heard already, throughout the day. This is starting from AM62X, 62A, these are Citara lineup of processors, going all the way to high-end 6.8, TDF4 VMID, and AM69. And you can see in terms of TOPS, in terms of the number of cameras it can handle, onboard ISP processing, specialized vision processing, GPU, video codecs, and so on, right? So this is probably one of the starting of the spectrum where you can run some analytics on the ARM, going all the way to offloading them to specialized hardware accelerators. So we would like to offer across these different solutions a same experience and the same set of tools that will help customers choose what they want and also port their software stack seamlessly across these devices as they apply it from one problem to the next. That's what is called as Edge AI SDK. I'll talk more about it. I hope most of you got an opportunity to go and see some of the demos we had in the AI demo room just outside this lunch hall. So pretty much most of the demos that you see there was put together by my team. We want to demonstrate and showcase how easy it is to use our SDKs and put together simple stuff where you can detect anomalies in your assembly line. If you want to classify, among 100 objects, you want to detect free space, anything with respect to perception, which involves a typical camera capture, inference, which is running your network on the target. And here we display, because it's a demo, but actually this information is taken forward to do next level of processing, such as sensor fusion, localization, path planning, and eventually control, which is actuating a wheel or something, a lever or something else. We want to give this experience and stay very much within the boundaries of open source. We don't want to provide something custom that has a very long ramp, to understand, comprehend, and start adopting it. So we want to give a very familiar look and feel, and that is provided via these popular open source runtimes, TF Lite runtime by Google, ONNX runtime, GStreamer, and OpenVX. So most of the theme of today's presentations you might have heard as how easy it is to use all the SDKs by packaging a bunch of tools. So tools is the main focus for us as well. We want to, at least we have packaged tools to help you throughout the journey, right from the time of, you've decided to train your model, you have data with you, you have probably 2 lakh kilometers of data captured by your car, or images, satellite images of some landscape, or your assembly line, anything, right? So data is not really in short of, some of them may be structured, some of them may be unstructured. It's easier definitely if it's structured. So we provide tools to take the data and start training your own model. Usually those who are new to this field, they'll try to use some of the existing popular models, some of the state-of-the-art models. So those models would have been trained on very high-end GPUs or cloud, which is not really an embedded specific model, right? So it will have its own power constraints. It will be full precision, full, either single precision or double precision numbers. You might not need something of that scale. You need something at a fixed point precision of 8-bit or even less than 8 bits, 4 bits, or even binary networks of 2 bits. So we give models to help you import from a cloud or a server to these devices by providing certain tools which will help you quantize and and make it optimized to run efficiently on the target. We also provide a superset of popular models, and we club it in something called as Model Zoo. At least as of today, we have about 40 models per device type, and we hope to provide you more than 100 models in the coming months for each of the device. In terms of inference tools, we provide something called as a model compilation tool. So when you have a model which you have explored, you have spent enough time with it, you have classified, you have trained it to classify your own set of unique classes, because if you take any off-the-shelf network, it would have trained on something like an ImageNet or a COCO dataset, which would have looked at a lot of 1,000 objects, mostly cats and dogs, or detecting pedestrians or vehicles and so on. But you might have different objects that is very unique to your problem that you're trying to solve. So once you have that network trained, you'll have to go through a compilation step to get it running on the device. And this compilation step is something that you run on a PC. It's not really on that embedded device. Once you have the model ready, you're ready to go and run it on the device. We only expect the artifacts coming out of this compilation step. We take in those artifacts and we take care of dispatching it to the underlying hardware accelerators. So one key feature of TI SoCs is it's very heterogeneous in nature. So you have really made a good job of porting your algorithm or your solution on our device if you have offloaded maximum compute to our underlying hardware accelerators or the DSP and run very less on the host application processor. So you can go take a look at any of the demos that we are showing. The load on the MPU core or the host core would be much lesser than the load on the rest of the cores. And that is how you take the maximum advantage of all the underlying cores that we built in the SoC. So we take care of running that. We care doing the task partitioning, the load partitioning, load balancing. Everything happens under the hood by supporting these inference runtimes. Now all of this is packaged together in what is called as Edge AI SDK. So just running the model is not the end of the day, right? So you need to connect it with real inputs, a real-time input like a camera or an audio signal or a LiDAR signal, run some inference on it, get some detections on it, and then you take the next step or the next decision. Now, to get all of you a flavor of how we can go through this journey, we have put together an integrated environment. This is also one of the demo in the room, which is called as Edge.ai Studio. Now, you can purchase an EVM, or even if you don't have an EVM, you can go and explore the tools that we have, where even if you don't know about how to go about using AI for solving your problem, but if you have just data, you can go and try that tool and see how far or how well you can do by applying AI. So these are different workflows. This is called as bring your own model, where you have spent considerable amount of time training your model to solve the problem. Then train your own model. So the train your own model is when you use when you have enough data, you have spent some time training your models with this unique set of data, and then you plug into this, bring your own model. Now you have a model ready that you go through the compile stage to import it. You can do a PC-based validation. Then if you want to iterate over improving your accuracy, because once you go from a floating point to a fixed point, there are quantization losses. So you need to trade off performance versus accuracy. So you might have to iterate it quite a bit to really get to that sweet spot that will get you running optimally on the device. And last is you bring your own data, where you really don't have much experience doing all these tasks, but you have data and it is in some structured way that can be fed to the tool. Then you can use this Edge.ai Studio tool to annotate right from the step of annotating the data as to what are the objects that you want to identify, what are the different classes that you might want to look at, train the network, compile. Everything happens in the cloud, and finally we get a preview and a model that you can deploy on the edge. Okay, so that is what is Edge.ai Studio all about. Basically, this is a sort of a no-code GUI-based tool. You don't need to write a single line of code. You can train a model end-to-end, and then have it, with a click of a button, it will go and deploy on your device. We also have a command line-based interface for those who want to automate this or get some more insights to how, what happens during training or the compiling phases. And a model analyzer tool where you can go and analyze from a standard list of 40 models as of today, which will increase more. So this is some 40 models supporting 2 different task types, that we plan to add more task type like key point detection, semantic segmentation, and add more devices in the future, support more devices in the future. So model analyzer is a very useful tool where there are customers who would take an off-the-shelf model and modify it, change its layers, change the connections a bit to get a better result than what it is designed for. So for such folks, that model is the IP. It's their intellectual property. So they don't want to share the model with any silicon provider or any open source people. So how would you evaluate the performance, right? So you have a model, you want to know how well it runs on the device. So from a list of models that we have, you can plot an accuracy versus performance, and you can try to match closely to an architecture of an existing model to what your model looks like, and you can get an estimate of performance and accuracy that you might expect. Also, in terms of the number of operators that we support, it's a growing list once again. Probably as I speak, there's a new YOLO V9 network that is coming up. The pace at which these things, we are getting new network architectures is really mind-boggling. But the interesting concept is that everyone is now listening to academic research, right? So you have premier conferences like CVPR and other important avenues where the latest and greatest network, which has improved accuracy by 0.0025% is there, and everyone wants to run that network. to solve their problem. So it becomes a challenge because the new network would have some newer operator types, newer layers that may not be supported by everyone. So we may not have YOLO V8 support today, we may not have Visual Transformer support today, but it is definitely in a roadmap to put or add those layers, and we'll see that come out at least a few months from now. Okay. So once we have all your network ready to go, a typical use case what we have seen is a camera runtime, some kind of custom processing using OpenCV, or your own custom kernels that you might want to optimize using ARM Neon, or if you really dare, maybe a DSP optimization if it's in your DNA. And then send it out to an output like a display, or you want to encode it and stream it out or store it. So these are some of the very flexible use cases that you can put together, but typically it falls into this kind of a flow. Out of the box from our SDK, we support these different type of inputs and outputs and these runtimes. But there is also a path if you have definitely a path when you have your custom sensor, your camera that you have. There's a path where you can either use the onboard ISP or it's a smart camera with its own ISP where you can bring in the data and send it through this pipeline. So this is how our integration stacks up. So no matter what device that we call it as an analytics device, it mostly integrates as shown here. At the base level, you have all the low-level drivers, your FreeRTOS running on your remote cores, some kind of a HLOS like Linux or any safe RTOS that you might want to consider for your product. Right, so this forms sort of a foundation or a must-have before you start writing any of the high-level applications. You need a sort of a middleware. In our SDKs, OpenVX has been the popular choice of middleware. Almost for more than 7 to 8 years now. It serves a lot of different functions and use cases, and it is very OS agnostic. You can develop using Linux and then later switch on to a safe RTOS if you prefer. The application, all the code that you would write, everything would remain the same. But it is also a channel where you can communicate between different processing nodes. I have a slide on that. We'll talk about it. But what we offer in the AGI SDK is not writing an application in OpenVX, but something even more friendlier and more familiar called as the GStreamer framework. So how many of you know GStreamer? It's been there for more than 20 years now. It's one of the most popular streaming media framework, mainly for streaming audio, video application. Most of the players, popular open source players also built on top of that. So GStreamer is extremely flexible, extremely powerful, and you can customize. We've used that to give you a very simple and seamless access straight to a hardware accelerator or a deep learning accelerator or a vision processing accelerator or a GPU or a codec, right? So and once you have that access in the form of a plugin, it's called a GStreamer plugin, you can connect these plugins back to back and bring up a use case. So as this forms the horizontal, the vertical is the analytics stack, the imaging stack, and the networking stack. They intersect pretty much every layer of the software stack, right from the middleware, from the application to the low-level driver. And what puts them all together is the application stack. So just a quick view on the application stack. So these are our spectrum of devices that we saw. So we sort of offer 3 flavors. One is an ARM-only stack where you can run pretty much whatever you want on the ARM, right? So this is not really a device differentiation, but this is something that you can easily do on this anything ARM only because everything is open source right here, right? With respect to the accelerator-based devices, the AGI SDK highly recommends using GStreamer-based design flow. We provide Python and C++ reference examples. We also have a flow called as OptiFlow, where you don't have to write a line of code if you know how to construct a GStreamer pipeline. You can bring up a 16 camera with AI display use case, in a matter of minutes. Or even if you don't know how to construct a GStreamer pipeline, there's a tool which translates a config file to a GStreamer pipeline that helps you run that. That would be the most optimized data flow, AI-based data flow that you could do on the device. And again, staying very much within the open source realm and provide acceleration, very seamless way to access all these different underlying accelerators. What we offer specifically for automotive is the OpenVX stack, where the application itself is written using OpenVX. Again, most of the automotive customers want some sort of a safety OS running on their application processors. They want to have that flexibility to switch between Linux-based development in the early days to an RTOS-based development towards the production state. So that's another flavor that we provide as well. A very typical data flow, again, just going one level deeper into that camera AI display chain. So you'll have a sensor. This is IMX209 is a popular Raspberry Pi V2 camera. So it's, if you can grab a Linux driver for it, it comes up as a V4L2 source. You can query the sensor for a certain resolution and a frame rate, and you can grab all the raw frame to come and reside in the DDR. And then the ISP, which is the onboard ISP, which is there in something called Vision Imaging Subsystem, VISS. It reads these raw frames and gives you out in the color format of your choice, NV12, RGB, monochrome, whatever you want. Then if the camera has a fisheye lens, then you can rectify it using lens distortion correction engine, LDC. Then resize it to the size you need to run to the network, because every network is trained for a certain input size. NV12 is the most common embedded friendly format of if you want to represent a color image. We usually don't process in full RGB fidelity, it's compressed to NV12. But the networks are mostly trained on RGB, any of the popular networks. But you can add a layer to accept NV12 and then convert to RGB if you want. So you can do either as a pre-processing or have it inside the network itself. In most of our demos, we want to overlay whatever the network infers. So we draw out another resolution from multiscaler, can provide you up to 5 separate outputs. We draw a parallel resolution, which is slightly bigger than the original resolution. We do some post-processing. In the post-processing, it could just be an overlay or a pixel-wise coloring for semantic segmentation or key point detection. Then we mosaic it in a background of 1920 1080 display and send it out. So this is the high-level data flow of every single demo that you might have seen in that room. We also have something called as a developer zone. You might also hear it as a marketplace. We have seeded it with some of these demos. Some of them you would have seen there. But we highly encourage folks to try out. This is in GitHub. You can fork some of these repos and try out your own specific use cases. If you want us to host your demos, if you're okay for us to host it, you can put in a request and we'll be hosting it under the Texas Instruments page. So it's free for all. We hope we have made it simpler enough for you to just drop a model and do any kind of deep learning processing or any kind of inference that you might be thinking of. Yeah, that's mostly what I had. That would hopefully maybe open up for some questions.
The audience?
We have one over there.
As you already told, GStreamer is like quite old already. But what's new in the Edge AI GI-PI streamer pipeline for the processors without having the hardware acceleration?
Yeah, there is no, as I mentioned, there is no differentiation for. So our contribution is integration with GStreamer and underlying, our middleware is OpenVX. So that is the part where we have taken a GStreamer buffer to pass it without copying around between multiple accelerators. So it is a zero copy design, zero buffer copy design. And for cores which has no acceleration or which does not intend to use any of the underlying accelerators, there is no differentiation or specialization from our side.
Any insight on, like, if I just compare AM62 without hardware or AM62A, what is the performance, single core performance difference for just the pipeline you saw?
Yeah, so pretty much all the blocks that you would have seen.
Because most of them are like hardware accelerated blocks, which you're
Yeah,
using.
so the dark blue ones are the ones running on the ARM. They are the only ones running on the ARM. The rest of the stuff is all offloaded. And that is how you use a TI processor. You have to offload as much as you can to the underlying accelerator. So if you have ARM-only solution, every single block will be colored dark blue, and you probably won't even get more than 1 FPS. And if you get 1 FPS, that's great, again, depending on the type of image or the network that you're running. So AM62, again, this is not a compute, okay. It's a fine line between compute heavy versus IO heavy. So AM62 has 1600 MTS DDR, whereas 62A has 3200 MTS DDR. As you go higher, you have higher clock speed DDRs. Your DSPs and accelerators are run at the C7X DSP, which does the matrix multiply, which has the matrix multiply accelerators, does your DL acceleration is clocked at 1 gigahertz. Your flavor of application processor differs from AM62A to 68. 62A has quad A53, whereas 6869 has quad A72s. No, 68 has dual A72, 69 has 8 A72s. So there are differences. And in terms of TOPS capability, AM69 is the highest, doing 32 TOPS, whereas AM62A is doing 1 to 2 TOPS.
Thank you.
So the performance you told it is 1 FPS, is it, for 62A?
I'm sorry, I didn't get
Performance you just told it is 1 FPS.
Yeah.
It means that input output delay is 1 second?
No. So 62A, no, I was talking that for 62, not 62A. 62A is the accelerated device, which has the DL acceleration inbuilt. This does have C7X MMA running at 62A is the device with the DL acceleration. 62 is the device without any acceleration. So your entire application stack runs only on the ARM core. Here you can offload it to the DSP core and the other accelerators that we have underneath. So we have shown, even in our demonstrations, that you can do at least 30 to 60 frames per second real time, again, depending on your applications. We have customers who built up, what you're showing are simpler ones. We have customers who built a full in-cabin sensor, in-cabin monitoring solutions with driver monitoring, rear passenger monitoring, with DL load going all the way up to 2 TOPS. It's a very complex use case and application built using GStreamer, running very much taken to their production device.
No, you mean with AI at 30 frames per second is okay with that AM62A?
Yeah, very much. You can even do 120 frames per second if you want, but again, depends on your model complexity, your input frame resolution. So clearly you cannot do 8 megapixel 120 frames per second, but maybe you can do a VGA 120 frames per second or something lower resolution. Most of the solutions begin like that, where they get a very high megapixel camera but they waste most of the resolution and they either downsize it or they do an ROI, and what they can really do is a very small ROI for a network. So it's very use case specific, but your available budget is 2 TOPS. You have quad A53 cores running at 1.4 gigahertz. You have a DDR clocked at 3200 millions of transactions per second. So this is your budget, so you need to fit your use case within that budget.
Thank you.
Okay, thank you.
Thank you for your questions. I'd like to express our gratitude to Shyam for taking the time to share his knowledge with us. Shyam has been at the forefront of TI's Edge AI revolution. So thank you so much for your contribution, Shyam.